Hi guys, thanks for tuning in. So we are currently discussing two types of convergence notions. The first one being the weak convergence, and then at the end of the last video we defined the so-called weak star convergence. Now up front on the surface they seem to be quite different things, because the weak star convergence makes a statement about convergence of elements, sequences more precisely, in the dual space, whereas the weak convergence makes a statement about convergence of, well, vectors in the original space, right? However, remember that the dual space is always a normed linear space itself, because you can equip it with the operator norm, and the vector space structure is inherited by defining linear combinations pointwise of two functionals, right? So that means in turn, if you start not with a normed linear space but already with its dual space, then you can compare weak convergence and weak star convergence, and in fact also the convergence type that we have used all along, the ordinary convergence in norm, right? So it turns out now that, having said that, we have three notions of convergence on the dual space of a nonlinear space, of an NLS. Okay, so here are the three convergence types. The first one, that's the one that we have been playing around most of the time. This is the just convergence in operator norm. So Fn converges, the sequence of linear functionals converges to a linear functional f in norm if, well, this statement holds true, right? Now the second notion is you can define the weak convergence on the dual space. All right, this is up here. So remember, weak convergence was if you have a sequence in your normed linear space. Now here this would be a sequence of linear functionals, right? Because we're working in the dual space. And then weak convergence of this means, well, you have to evaluate it on any linear functional on the dual space. Yeah, but these are then elements in the bidual. So that's why we have the two stars. And then weak convergence on the bidual would simply mean that this limit here, k of fn going to kf as n goes to infinity, holds true for all elements in the bidual. And that's precisely what's written up here in condition B, right? So this is simply translating the weak convergence that we defined a little bit earlier, not at the end of the last video, but at the beginning, and now rephrasing it in terms of the dual space, all right? And then finally, what was the last definition at the end of the last video was the weak star convergence, right? So fn x minus f of x in the underlying scalar field goes to 0 as n goes to infinity. All right, now you should think of this really as a tower of convergence types. So the first one, that A convergence in norm, is the strongest. So maybe I will draw an arrow here from A, because why is this? Well, we already discussed this, that norm convergence, the ordinary convergence, always implies weak convergence. So let's write this out one more time up here. So if you have this one, you just use, well, the linearity of that element in the bidual, and then you do the ordinary trickery with the norm, right? So, and now if you have norm convergence, this one here on the right will go to 0, hence the thing on the left has to go to 0, right? So clearly A, that is norm convergence, implies weak convergence in the dual space. And the same is true further downward, namely that weak convergence in the dual space implies weak star convergence. Why is this? Well, you have to read the statement carefully. So converges weakly if and only for all elements in the bidual. Yeah, but remember, there's one element in the bidual that plays a huge role, which is the image of the canonical map, right? That sends vector x to, well, this j sub small x, and that acts by pointwise evaluation, right? So if condition B holds true for all elements in the bidual, then it has to hold true in particular for this element, right? Yeah, but now remember how it was defined. It was precisely defined as pointwise evaluation on the point, right? And that's precisely what's written in condition C, right? So weak convergence in the dual space implies weak star convergence. So it's really a tower. C is the weakest, and then you can make your way upward or downward. All right, before we gather some more properties about the weak star convergence beyond the definition, let's do an example here. So we consider non-linear space, the NLS X, continuous functions here, you know, from -1 to 1. Usually it was 0 to 1, but doesn't matter as long as you're compact. As long as you have a compact interval there on the real line, equipped with the infinity norm. And now we define this, well, sort of element, rho sub nx. Maybe I'll move the star away because I want to draw a picture. So it is, we'll draw a graph of it. So x, y. So you have somewhere 1 and -1, and then here is, well, outside 1 over n, it is equal to 0. It is continuous. You can just plug in t equals plus or minus 1 over n. You will get n minus n squared times 1 over n. So this is n minus n. It's equal to 0. So the sided limits match. So this is indeed a continuous function. And how does it look like? Well, it is 0 here and here. And then at t equals to 0, it is, well, equal to n. And then it is, well, connecting it with straight lines, right? So this is sort of a triangle thing, yes? Notice, by the way, here, the way it is constructed, so the area that it encloses, the green shaded thing, is precisely equal to 1, right? Because the base has length 2 divided by n, the height is n, so, and then you have 2 over n times n is 2, and then times a half, it's 1, right? So the total integral, maybe let's write this out because I will use it. So rho nx dx is equal to 1. Okay, good. Now I want to make a statement here, so I want to make a statement about weak star convergence. So here it will be the sequence of linear functions that we're working with, fn of x, which is, well, kind of the antiderivative of an arbitrary continuous function g, but weighted with that rho n of x. All right. So now let's do some computation here. So this is clearly a linear functional on acting on continuous functions supported from -1 to 1. It spits out a scalar which is finite because you're integrating two continuous functions there over an interval of finite length. So that's going to be finite. Everything is well defined. And now let's do a little computation here and obtain. So I want to figure out whether my sequence here converges weak starly to something, and it does. Obtain for every g in c minus 1, 1. Well, what would we expect? Well, so if you look at the picture up there, as n goes to infinity, of course, this base is here going to shrink down to 0, whereas the height grows all the way up. So it's going to very much be like a delta. If you ever heard what a delta function or a delta distribution is, that's kind of what this thing will shape up to. So maybe what will happen is, at the end of the day, everything is concentrated around the origin, right? And so indeed, let's do this. So let's do fn of g minus g of 0. Okay. Now that value is finite because g is continuous from -1 to 1. So g of 0 is certainly finite. And now what do we have? So by definition here I have g of x. And now what I claim to be true is this is just equal to g0 rho n of x dx. And why is this? Well, because of linearity of the integral and the fact that my weight rho n of x has total mass equal to 1, right? Because this g naught here is a constant. It doesn't depend on the integration variable, so you can pull it out of the integral, and then what you have left is precisely that green underlined thing, which is equal to 1. So this is an equality here. All right. Good, and now you can estimate a little bit. Notice this rho n of x only kicks in the interval from -1 over n to 1 over n. Outside of that, it's equal to 0, so that means my integral here I can run from 1 over n to minus 1 over n. And then what I will do is I will go with the absolute values inside using the triangle inequality for integrals. So I have gn of x minus g0. Rho n of x doesn't need an absolute value or complex modulus because it's non-negative function, as you can see up there in the picture. All right, so you have this, and now what you can do is the typical trick. You optimize this, so you can write this is less than or equal than the maximum x taken over this interval, gn of x minus g of 0. This now, after taking the supremum, or the maximum rather here, because continuous functional compact interval supremum is the maximum, you can then also pull out of the integral, and then what is left is just the integral of rho n of x from minus 1 over n to 1 over n. Yeah, but that's 1. That's that green triangle up there. All right, so what you have is this is simply less than or equal to this maximum here. All right. Yeah, but now look what happens. So when n goes to infinity, there's no, oh, why do I put a subscript here on the g? There's no n dependence in the g here. This was correct up here, but here I put n's, right? So let's correct this. It's just g of x minus g of 0. Okay, yeah, that's better. Now, so having established this, put it here. So now what I will do is I will send the n to infinity, and then what happens here in the supremum? Well, when n goes to infinity, of course, everything shrinks down here to 0, and since g is continuous at 0, that thing here, g of x minus g of 0, that will go to 0, right? This is just continuity at the origin, right? So this thing, as n goes to infinity, it will go to 0. Okay. In short, what we have just proven is the following, that my sequence fn converges weak-starly to the linear functional f that just evaluates a continuous function on minus 1, 1 at the origin, g of 0, right? Because this is precisely what I subtracted here. This is my f of g, which is pointwise evaluation of g at 0. All right? So there we have it. So this sequence certainly converges weak-starly to this linear functional. Now, as it happens, however, I won't show this, and I will say why. This same sequence does not converge weakly to the same linear functional. All right. Why am I not discussing this? Because if you want to investigate weak convergence on the dual space, then you should have some idea how the dual space looks like. And we have not computed the dual space for the continuous functions with a supremum norm. And we haven't done this because this requires integration theory. This module here does not use measure or integration theory. All right, that's why I didn't do this. Maybe there will be some exercise preparing some of the background, knowledge that would allow me to prove that this convergence is not weak, but it won't be part here of the videos of the lecture. Okay, but you can take my word. This same sequence does not converge weakly to F. Okay, let's do instead an example where we can prove everything. That will be a sequence space, because there we have some experience with dual spaces and biduals, right? So consider the NLS X, which is, well, sequences that converge to 0 equipped with infinity norm. Now we know the dual space of this guy is isomorphic to L1. We know there exists, this was one of the examples in the section on duals and double duals. There exists an isomorphism T from L1 to the dual space. L1 just equipped with the ordinary 1 norm. And we know that this is a result of having proven this first statement, we constructed that isomorphism explicitly. every linear functional on C0 is of the form, well, this, what I said is sort of motivated by inner product formula, although it's not an inner product. Xn, Yn, where X is any sequence that converges to 0 and that little y is in L1, right? With a unique y, which depends on the linear functional, of course, sequence in L1n. All right, so now we will gonna look at the following sequence of linear functionals. Consider the sequence Fen. So remember En, those are our favorite kind of basis vectors. N1 infinity, C0 n. So you take this guy up here with the yellow star and you substitute for y the E sub n's. The E sub n's, they are you know, all in L1, so that's all well defined. Then what do we get? Well, I claim that Fen of x, well, you just substitute it in the formula. Since it's En, only one term survives, and that what it does is it precisely projects onto the nth x sub n, right? Yeah, but x is a sequence in C0, so as n goes to infinity, this guy by choice of x goes to 0, right? So that means in turn that Fen, and this is valid for all x, in C0n, so the sequence Fen converges weak starly to the zero functional, on Z0n, right? So the zero functional certainly sends everything to 0, and what we will prove in a few moments is that weak star limits are also unique. Okay, so that's why I can conclude here that sequence converges to the zero functional. Okay, good. However, now we will show that the same sequence does not converge weakly. Does not converge weakly to the zero functional. Okay, and in that sense, C, remember that tower of three convergence types, the one on the bottom is really the weakest, okay, among all the notions of weak convergence that we now know about. Does not converge weakly to the zero functional. Yeah. Okay, so why is this true? Well, first off, we also know something about the dual space of L infinity. So there exists an isomorphism, call it S, from L infinity n to, well, no, maybe I should formulate it differently. We actually don't know the dual space of L infinity. That's also quite hard, but we do know the dual space of L1. It is isomorphic to L infinity. So if you look at the following composition, you take the dual transformation, its inverse, and then hit it with S. So that's going to be a map from L infinity to the, well, bidual of C0, right? You're going to need this map because if you address weak convergence on the dual space, here, remember my space is X. Up here, this is sequences that converge to 0, so I need to get my hand now on the bidual of that guy, right? That's why I construct this map down there, because this gets me to the bidual, all right? So, is an isomorphism, all right? Hence, what does this mean? Hence, we know any k in the bidual of Z0, there exists a unique well, what I'm writing out now is just the definition, what it means to have an isomorphism. Anything here on the right is coming from a unique starting point here in the left, right? There exists a unique yn sequence in L infinity, so that K is T dual transformation thereof inverse Sy, okay? Which implies the following. Well, KFEN, that's something what I want to say about, is what is equal to T dual inverse Sy evaluate on FEN. Now you do the typical trick. You swap the dual here and the inverse, and then you use the definition of the dual transformation. So this is Sy T minus 1 FEN. But if you remember how T acts, T, this has to do with this formula up here with the yellow star. So now what T inverse FEN does is it just assigns it back to the EN. We discussed this multiple times when we did the examples. So I will just say by yellow star, more precisely the definition of this isomorphism T. This is just Sy En, all right? Yeah, but what is Sy? So S is a S maps an element in L infinity to a linear functional on L1, and we know precisely how those linear functionals look like because we identified the dual space, right? So this here, by the same reasoning that we also applied in the section on the dual spaces, is just the nth entry of the vector y. Yeah, but this one in general, because y is just in bounded sequence in general, as n goes to infinity, this does not converge to 0. Okay? And that's what you wanted to prove, right? So that's why the convergence does not hold in the weak sense, because if it were to hold in the weak sense, then this one here, the pink underlined one, as n goes to infinity, has to go to 0 for any k in the bidual. And here I argued why it does not, because your yn is not a sequence that goes to 0, it's just a bounded sequence. There's no reason why this guy has to go to 0. Okay? All right, which implies this. Okay. Yeah, and that's it. That's it. Right, so the convergence does not hold in the weak sense. Okay, good. Remark. So, maybe I will go back to the list of these 3 convergence types and make the remark there. So we had this one up there. We argued why B implies C, because you can just hit it with that canonical, that image in the canonical map. But now, when do we have C to B? Is there a case that we know about where this actually holds? Well, remember reflexive Banach spaces. So in reflexive Banach spaces, all these elements K are of this type with some, vector X, right? So if you have a reflexive Banach space, then weak and weak star convergence on the dual space are actually the same. And right now it should make sense why these examples there failed that I just did, because we already proved that C0 of n is not a reflexive Banach space, right? So you should not expect this. All right, that's one remark. So in reflexive Banach spaces, there's no distinction between weak and weak star convergence on the underlying dual space. Now, finally, let's summarize some of the properties of the weak star convergence. So theorem, I can probably just write it out and then prove it early on in the next video. Let X be a NLS, X star its dual space, and Fn a sequence of bounded linear functionals. Now if Fn, okay, this I already proved earlier, B implies C. If Fn converges weakly to F, then Fn converges weak starly to F. This I already explained why this is the case. You just take the image of the canonical map. Furthermore, weak star limits are unique. That is not hard to see. And now the last part, that is more interesting. And if X is complete, aka a Banach space, and Fn weak starly convergent, then it is bounded. Right? So that's the same thing holds true that you had for weak convergence. Right? For weakly convergent sequences, also there the sequences were bounded. And here's the same. For weak starly convergent sequences, there exists positive C, so that all your Fn's in operator norm do not exceed that constant. All right? This will be once again an application of the principle of uniform boundedness. All right, so I'll prove this in the next video early on. There's only a few parts that we still have to prove, and then we will move on with the theory of weak star and weak convergence. I'll see you soon.